Hello, and thank you for choosing to join us for this presentation today. My name is David Stowe. I'm a product manager at Gatan for SEM products, and today I'm going to be talking about recent advances in cathodoluminescence microscopy. Now, I'm hoping that many of you who chose to join us are familiar with the technique of cathodoluminescence, or CL, as I'll refer to it, in the majority of this presentation. But in case there are a few of you who are not familiar, then I'll give a quick introduction for a few slides before moving on to some of the developments that have been happening at Gatan and with our customers in the last 12 months or so. So cathodoluminescence is a technique which allows you to correlate the optical and structural properties of a material down to the nanoscale. And to do that, we use an electron microscope. Typically, that's a scanning electron microscope, an SEM. And the electron gun of the SEM excites the specimen, stimulating a number of signals to be emitted that we use for analysis. That's either structural analysis, looking at size and shape of the specimen, or composition. But there is another signal that we often ignore as microscopists, and that's a signal that is cathodoluminescence, and it's light. That light that's emitted, it's part of the electromagnetic spectrum, infrared, visible, and ultraviolet wavelengths, gives us information about the optical and electronic properties. And when we attach a cathodoluminescence detector to the side of the microscope, we're able to analyze the properties of the light that are emitted. And because we're using an electron beam as the excitation source, the stimulating input energy, it's actually the interaction of that electron beam with the specimen that determines the spatial resolution, not the classical optical diffraction limit that you think of in optical microscopy. So this really allows us to start interrogating optical properties down to the nanoscale. And of course, then to extend that into correlation with all those other signals that we can get in the electron microscope. Now, when I refer to analyzing the light that's emitted, conventionally, we think about this in terms of understanding the spatial variation in the emission, so how much light is produced at each pixel in an image, or what light. So what's the wavelength or energy of the light is emitted? What's the color that's been emitted? And that spatial and spectral information can also be captured together in the same data set in a form called hyperspectral imaging or spectrum imaging. And these three different types of analysis allow us to understand the variation in the emission centers in our material. It could be trace elements or crystal defects in the material or impurities. And of course, then understand the mechanisms behind those emissions too. So we can understand the electronic band structure of semiconductors, for example, look at the local density of optical states, or identify the emission centers in the material. And of course, when you have spatial and spectral information together in the same data set, then you can start mapping these and reveal things like compositional variation, stress, phase distributions, etc. So it's a very powerful technique to get optical information, both spatially and spectrally. Now, depending on the exact type of sample that we look at, there are a range of different mechanisms that can give rise to what we would broadly term cathodoluminescence. And so you really have to understand a little bit about your sample in terms of its makeup, and to really be able to interpret what is going on based on the cathodoluminescence information. But we can broadly split that down into a couple of major sort of materials categories. And if we think about metals, noble metals in particular, then we start thinking about plasmon effects that give rise to decays that emit at optical frequencies. And here we can really start to study things like the interaction of light and matter at the nanoscale and reveal the local density of optical states, for example, or characterize it in terms of an energy momentum spectroscopy. So a very powerful tool at looking at the optical properties of particularly metallic nanoparticles or structured materials at the nanoscale. More classically, we would think of materials which have an electronic bandgap that give rise to classical luminescence. And so the emission that we see here is due to local variations in the bandgap, for example. So we're looking at semiconductor materials, primarily compound semiconductors, that are used for optoelectronic devices, transistors, a wide range of materials, novel two-dimensional electronic materials and things like that. And these have very real applications, in solid-state lighting or display technologies or photovoltaic devices. And then if we look at ultra-wide bandgap materials, getting towards 6, 7, 8, maybe even up to 10 eV, then we are starting no longer to look at the bandgap information at the optical frequencies that we can detect in CL, but rather structural defects, so things which put electronic states into the forbidden bandgap of the material. So these may be rocks, minerals, and gems, where transition metals introduce color centers into it, and we can characterize those materials, understand the temperatures and pressures that they were formed under and of the types of conditions that they've been exposed to understand the geochemistry of a material. Or it could be more material science-based applications where we're looking at things like single photon emitters for quantum cryptography and quantum computing. So a very wide range of applications. Now, about 2 years ago now, we introduced the Monarch cathodoluminescence detector, a couple of various flavors, but the Monarch Pro in particular really redefines what's possible in cathodoluminescence microscopy. So it delivers unprecedented sensitivity. So by that, I mean it gives the highest quality spectra and images in the shortest time. And really importantly, it has easy operation for all of the users who come to use the tool. And I'll talk a little bit more about why that's important in a few more slides. Delivers brand new analytical capabilities to give you the most complete understanding of CL to date. And really rather importantly for this sort of microscopy setting is that we have really accurate correlation with other signals in the SEM. And so we can detect many of the electron signals with the Monarch detector, and also in some cases with some optional components, then we can also perform EDS simultaneously as well. And again, I'll show you an example of that in some later slides. But let's start and let's look at this, the first bullet point on this slide, and we talk about the unprecedented sensitivity of the tool. Here is very much the same samples that I showed you on a previous slide about the common modes of CL, of operation for CL, but this really demonstrates the improvement in the quality of the data that you can collect with the Monarch detector. So a vastly improved signal to noise ratio in our images, sharper spectra, so taller and narrower peaks are able to resolve much more information, able to then map, perform hyperspectral mapping or spectrum imaging at a much faster rate, or analyze materials which are more beam sensitive, for example, fluoroscope materials. And I think this slide really emphasizes the step change difference that this improvement in quality allows you to do in terms of what data you can capture from a sample. So these two data sets show actually with our previous generation system, which was world leading at the time it was available on the market compared to the Monarch. And here we are looking at a two-dimensional material, so hexagonal boron nitride that's ultra wide bandgap material, so 6 electron volt bandgap, so emits a deep UV wavelength, something which is traditionally and conventionally very difficult to analyze spectroscopically. However, you can see immediately a huge improvement in the signal to noise ratio of the Monarch image compared to the previous generation tools or other tools that are available on the market. And that, of course, then allows you to perform spectroscopy from either a single point or extend that into mapping where we are really able to understand, in this sample, the different exciton behavior as a function of position within the sample. So we have a number of different electronic processes going on in here, including a number of different exciton recombination pathways, but also point defects as well. And we're able to map those out, over this relatively large field of view in just a few tens of minutes. So it's a real dramatic improvement in your analytical capabilities compared to other systems. Now, not only do we have this superior optical design, we really threw away everything that was kind of known about cathodoluminescence detectors and started from the ground up to really design an optical system which was completely unsurpassed by anything available on the market. And we've done, I have to say, a great job in that. However, that's not the only thing that drives improvement in the data that you can collect. Now, this is a slide that I have previously showed many times at a number of conferences around the world, and it demonstrates how in most specimens and in all other systems, you were really limited in terms of the quality of data that you could collect by your experience and expertise in using the system. And really, the Monarch tool introduced some features, which I'll talk about in a little more detail in a couple of slides' time, that really changed this whole idea. You no longer have to be an expert user to get expert quality results. The Monarch tool simply delivers that for you. So one of the things about cathodoluminescence spectroscopy is that you require exceptional optical alignment. And what I mean by that is that the sample must be located very precisely at the focal point of the CL system and co-aligned with the electron beam axis of the electron microscope. So it's three different systems we have to think about in terms of aligning, and aligning or misaligning by just a few microns dramatically reduces the throughput of the spectrometer. So dramatically reduces the signal to noise ratios you can see in these example spectra, where a misalignment of just 60 microns in one axis results in throwing away 70–80% of the light that you could have collected. And when we're talking about hyperspectral data acquisitions, which can take tens of minutes, sometimes even hours, this is a huge experimental time saving. But even more importantly than that, if we look at some of the advanced modes, you really have to have perfect optical alignment, otherwise the data that you collect is meaningless. So here is an example of angle resolved imaging, and I'll talk about this analysis mode in a few slides' time. But at the perfect focal position, so where the sample is precisely at the optical position of the CL detector, we have this perfect focus. We have this half moon shape with all of the light being contained entirely within that dotted line. However, even a misalignment of just a few microns in any of the directions results in the data that you collect being meaningless. So not only are we throwing light away because we no longer couple it into our optical system correctly, but we're also collecting data which is completely meaningless and no longer interpretable. So this is why the optical alignment is really, really important. And actually, it's something that's surprisingly hard to do. And this is the reason why in other systems, people have never been able to get expert results when they're learning how to use tools. So the focus of a CL system has a precise spatial location in X, Y, and Z, but there's no reliable method to find this. So it's actually pretty ineffective to use the luminescent signal from most specimens. They're either weakly emitting, you're trying to push the conditions to really improve the quality of the spatial resolution or the minimize beam damage or something like that, or they have large spatial or spectral variations which make interpreting the information that you see difficult, or it changes with time. And the electron beam exposure changes the signal in a number of cases, particularly with prolonged exposure. So one way that some people have suggested to do this is to rely on standard SEM parameters such as stage position or working distance. However, this doesn't work either. Those values in all electron microscopes that I'm aware of depend not only on the settings and the alignment that you have in the electron column, but critically and fundamentally important is one of the first things we learn about electron microscopes when we start learning about electron microscopy, that the depth of field of the SEM is much greater than in optical systems. So it means that it's fruitless to use a setup specimen. You can't simply, set up one specimen that's easy to do, rely on the SEM parameters and move over to the specimen of interest. This just doesn't work. And so all of the systems require a manual iterative alignment without there being a reliable way of doing this. And expert users can often spend maybe even several hours aligning a system satisfactorily. However, many users are unsuccessful. You may ask how the Monarch tool has changed this. Well, in the Monarch tool, we've introduced an automated, reliable alignment process that's independent of the user, the sample, or the SEM conditions. I know that lots of people immediately ask how this is done, and the flippant answer is that, well, you just click a single button in the software and it's done for you automatically. But I'd like to talk you through some of the steps in that process so that it's a little more transparent to you and demonstrates to you why it's independent of all these variables. The way that we do this is to initially turn the electron beam on and focus the secondary electron image, so we know roughly in whereabouts in the microscope the specimen is. This could have been just inserted into the microscope for the first time and be maybe 40, 50 millimeters away from its ideal location. And so we work out very roughly how far the sample needs to move, and we bring that closer to the collection mirror. And then we ask the user to focus the electron beam again, just to verify that we have brought it to roughly the right location. We then turn the electron beam off, and so we no longer rely on the SEM. We turn on instead a laser, which is built into the Monarch system. So we illuminate the specimen with a laser, and we measure the intensity of the reflected light. We then scan the specimen stage in the Z direction to determine the maximum of the reflected light. And at this point, we are able to determine the perfect focus position based on the profile of that reflected light. You can think of this in a way a bit like confocal Raman or confocal optical systems, where you have this ability to perform sort of optical sectioning in the Z direction. We're doing a very similar process here that allows us to very precisely locate the perfect focus position of the sample below the collection mirror. This is how we really deliver repeatable, reliable, and quantifiable data without relying on the use of the sample or the SEM conditions. And one of the ways that this makes a dramatic impact on the usability of CL systems in a laboratory is that now everybody who comes to use the tool can start collecting expert data in their very first session. So they're no longer having to learn about how to operate the system and to align it, which is a process that can take several months even for many people, but they can immediately start collecting data. And this is a slide I like to show because this is an example of data collected by a novice CL users within just a few tens of minutes of turning on the electron beam in their first session. And even with the latest systems that are available on the market or recent generations of systems, analyzing these types of samples was almost impossible. So this is a gold palladium nanostar. Tip to tip, it's about 100 nanometers in size, and it's being drop cast onto a non-luminescent substrate. So they're very dispersed. particles on a non-luminescent substrate, which makes that kind of iterative alignment procedure impossible to do. They emit with very low signal levels, and as I said, those intricate alignments are just almost impossible to do. And so many people thought that analyzing these sorts of specimens were just impossible with CL systems. However, the Monarch tool goes to show you that even novice users can now start collecting this type of data. In the center, we have a spectrum image, which also includes information about polarization, and you can see these two different dipole modes that are emitting with different polarizations from this nanoparticle. And you can also then look at the emission pattern. You see that we have the emission pattern where the direction of the light being emitted is actually orthogonal to the direction of the dipole mode, as we would expect. But remember, this is a novice user collecting world-leading data within their first session of using this tool. So not only is the system really easy to use, but we've also introduced a new range of analytical modes that can be used with the system. And I mentioned some of these briefly on the previous slide. So we can start looking at angle resolved, so determining the emission pattern from a material. But we can also extend that further and capture information about wavelength and angle in the same data set. So we can really understand how light and matter interact far below the optical diffraction limit. And of course, as I highlighted on the previous slide, we can perform polarization measurements too. So look at the emission polarization properties of these deep subwavelength structures, for example. And the polarization mode can be used in conjunction with any of the modes that I've described so far in this presentation. So to give you a little bit of background, angle-resolved cathodoluminescence is a method that allows you to determine the emission pattern from of the light emitted from a specimen. And the way that we do that is that we use a collimating mirror, so an off-axis parabola, open on one side, and an array detector, so a pixelated detector like a camera. And the electron beam stimulates photons to be emitted from the sample, and those emitted photons are transferred to the array detector through some additional imaging optics. And so the image of the mirror backplane is projected onto this array detector. And each pixel in that 2D detector image corresponds to a unique emission direction. And we can think of this as the zenith and azimuthal angle in polar coordinates. In fact, we would typically then transform this image into polar coordinates to make it more directly interpretable by a user. So we gather an emission pattern image that looks something like this in polar coordinates. Now, the information that you get with angle-resolved cathodoluminescence imaging here is an integrated intensity, so integrated over all polarizations and all wavelengths. However, we can extend this and analyze also the wavelength distribution by collecting something called wavelength and angle-resolved cathodoluminescence. And to do this, we use a similar setup, but this time we use an angle selecting mask to select a portion of the angle space from that image that's being projected from the backplane of the collection mirror. And we disperse that through a spectrograph, an aberration corrected spectrograph, to collect a data set which is dispersed by wavelength and has some kind of pseudo angle information. So we have a two-dimensional data set, which is wavelength and angle. We could then serially scan through the full angular range, collecting the entire angle space, so collecting wavelength spectra from each emission direction. Now, one of the reasons that this is really important is it allows us to start interrogating some really interesting properties about materials. And I'm going to introduce you to to an example of that in the following slides. So we can use this technique to determine the photonic band structure of a material with energy momentum spectroscopy. Now, the photonic band structure is a plot of frequency against wave number, and the photonic band structure can be thought of almost analogously to the electronic band structure. So it gives us information about how light propagates through a material or is emitted from a material. And in a photonic crystal, we can artificially periodically structure that material to modify the photonic band structure to introduce, for example, a photonic band gap. And this allows researchers and scientists to control the direction and wavelengths, or the way that different wavelengths of light propagate through a material. So this is a wide range of applications in optical detection and telecommunications, or high power lasers, waveguides, and particularly high resolution displays. I think this is something which is, I think, incredibly exciting. In the next 10 years, we'll see this introduced into a significant number of applications with augmented reality headsets and wearable devices. It's a really exciting arena for technology at the moment. And as an example of one of these materials that people are looking at in this sort of high resolution display, high brightness, high resolution display type applications, are sort of micro emitters, micro LEDs. So these patterned compound semiconductor materials that have a certain lattice arrangement where the emission from a single pillar is influenced by its nearest neighbor. So here is a really interesting use case of a material which has classical compound semiconductor luminescence, but also with this enforced photonic effect from this periodicity of the sample. So you look at these emitters, they are about a micron in size, so similar to the wavelength of the light that they're emitting at, and on a similar pitch. What we're actually looking at in the secondary electron image there is a tilted image, so that you're seeing the sort of height. So these are kind of 2 to 3 microns in height, with a diameter of the pillar, or a width of the pillar of about a micron, and the separation slightly smaller. Now, when we collect wavelength and angle resolved CL from these from this micropillar array, we see a number of really interesting effects. So on the left-hand side is a video displaying the emission pattern as a function of wavelength. And so you can see at each different wavelength or color within the within this wavelength and angle video, then we see unique emission patterns being generated at each wavelength. And you can see that in the images which have been extracted on the right-hand side of the slide, where at each color we see very distinct emission patterns. So it means that the color of light, the spectrum of the light that's being emitted in any particular direction, actually shows a strong variation. Now, these data sets can take a little while to collect. I mean, these are probably, this acquisition that I'm showing you here is probably a couple of minutes, but it's a relatively bright sample. But we capture this in a very highly parallelized manner and under complete software control. Now, once you have this wavelength and angle data set, you can then convert that into the energy momentum basis based on the periodicity and the directions of the lattice in the that hexagonal array that I showed you before. And when you do this for one particular direction in the crystal, you can see that we reveal the photonic band structure in the material in a given direction. And of course, you can, because we have this full angle information, we can look at this energy momentum diagram in any particular energy direction that you want to in the photonic band diagram. So we have this really powerful tool that allows us to determine, the photonic band structure of materials and to directly correlate that with the structural information that you see. So the uniformity of the periodicity of the shapes, or or whether directly understanding whether the influence of a missing pillar in the array or something like that. So it's a very powerful way of developing these advanced devices. Changing tact slightly, I do want to go over some of the advancements we've made in your ability to correlate the cathodoluminescent signal, which hopefully I've convinced you is a really interesting thing to collect in the SEM already, but how to correlate that information better with the other signals that are available within the electron microscope. Now, you've already seen that we use a collection mirror to collect a very large proportion of the photons that are emitted from a sample. And in fact, the solid angle of that collection mirror is something like 1.4 pi steradian. So we collect about 80% of the visible photons emitted from a sample, assuming it's a Lambertian emitter. But one of the consequences or downsides of using such a large collection mirror to make cathodoluminescence microscopy possible is that it blocks line of sight to many of the other detectors that you have in your electron microscope. So that could be the EDS detector, such as I have illustrated here, or a pole piece mounted backscatter electron detector, or it could be the in-lens detector. So you're often limited to working at 10, 12, 15, on some systems even 20 millimeters, which precludes the use of those in-lens detectors. However, the Monarch system has an option that allows you to collect or to provide line of sight to an EDS detector. And we also have software modules available that allow you to collect EDS and CL data simultaneously. So you can see now with that optional item or that optional collection mirror, we are able to collect EDS spectra within digital micrograph format. So the software program which runs the Monarch tool. Equally, I mentioned before that the mirror requires you to use a very long working distance. Typically, we've also developed that so that prevents you from using the in-lens, secondary, and backscatter electron detectors in almost all microscopes. One of the things that we've also added as an optional item to this system is an in-lens detector compatible collection mirror. So it has a smaller physical size, but also has been designed specifically to aid the transit of secondary and backscatter electrons back up through the aperture in the electron mirror, up through the pole piece to these in-lens type detectors. That'll then allows you to collect CL information and in-lens secondary or backscattered electron information from the same at the same time within the Monarch software. And I have a nice example of actually both of these developments on the next slide, where we have a meteorite sample. So this is a polished chondrite, a stony meteorite that is actually one of the earliest solids to ever form within the solar system. So it has all sorts of interesting information to reveal about how the solar system was created. And you can see that we have been able to collect both in-lens secondary electron image, EDS maps, and CL maps, all from exactly the same region, all with perfect pixel registration between these images, because we can collect those simultaneously with the Gatan software. So we have this perfect registration between different data types, and also allows us to avoid beam-induced artifacts from re-imaging the same location on the sample multiple times. You can see that the information that you get from EDS and CL, for example, although it is related, actually has some really nice differences. So EDS gives you major element information, phase information, whereas the CL gives you access to trace element chemistry. So it really allows you to look at some of the interesting geochemistry effects that happen during recrystallization or of the sample, or sort of metamorphism after it's first formed. Now, I would like to, I'm coming close to the end of the presentation. I hope that the interest in this presentation, if it's stimulated you to want to know more about cathodoluminescence and cathodoluminescence microscopy, I encourage you to visit a website that we've developed as an educational tool, which is whatiscl.info. It contains a lot of interesting information about some of the fundamentals of the technique, a lot of information about the applications, how people use this to answer a number of different problems from a wide range of different application spaces. It also includes tips and tricks and videos and instructional information, both in terms of hardware operation, but also data analysis too. So I strongly encourage you to look at this website if you're thinking of using CL, or you are a user, even an experienced user of CL tools. And then to summarize, reminder that Monarch, it's a relatively new system on the market. It really has redefined what's possible in CL microscopy, providing the highest quality spectra and images in the shortest time, brand new analytical capabilities and completely new insights into materials. That, for example, that energy momentum spectroscopy that we went through on an earlier slide. And this is available for everybody because everybody is guaranteed the best results with a fully automated alignment and some recipe-driven operation that's built into the tool as well. And of course, we're able to provide perfect pixel registration between all of those signals available to you in the SEM to give you the best, most accurate correlation with other signals. Okay, thank you for your time today.